Okay, our next speaker was gracious enough to give up some of his time so Lawrence Lessig's talk could go on. But it's time we get started because we're running a little short on time. Our next speaker is Luis Meraz. He has about 10 years of security experience and about 5 years doing reverse engineering of hardware and software. His presentation is on automated exploit detection in binaries. So please give a warm welcome to Luis Meraz.
Thank you. There was supposed to be 2 people to this talk. Matt Hargett is the other person that I'm working on this project with. He actually couldn't make it, but he wanted to say hi, and sorry he couldn't make it. And maybe he'll show up next time. But this talk's on automating exploit detection, or really looking for vulnerabilities in binaries by doing static analysis. There's been some work in this field. A lot of stuff is going on right now with source, looking through source for vulnerabilities automated. But this talk is going to deal exclusively with binaries, the types of problems that you run into trying to emulate and trying to predict branches and stuff like that, and what can be done and what can't be done. I'm not going to come up here and say that it's going to catch all the vulnerabilities and it's going to be, it's just going to drop ODE at you. It's not. It's going to catch some vulnerabilities, and then it's going to speed up audits, and it's going to get rid of a lot of low-hanging fruit and whatnot. More complicated vulnerabilities, that multi-step things, things where you're exploiting probably 2 or 3 vulnerabilities at the same time to be able to execute your code. Things like that, I don't know. Maybe it'll catch part of it, maybe it won't. That's a lot of why I'm working on this project. It's really interesting, and I want to see where it goes. So I'm going to talk a little bit about the definition, like some of our definitions, what the architecture is, and some of the challenges and the problems that come about doing this type of work. So the project is called Bug Report. It's on SourceForge right now. It's by no means a product or a real-world tool yet. It's just proof of concept code. We keep on working on enhancement as issues come up. And as I get into the architecture, really all it's going to be is going to be an emulator and some analysis on top of an emulator. And thanks. So it's all written in C#. This is actually the first time that I used C#. I wanted to use a language that ran in a sandbox, was able to run in Linux and in Windows. So everything that we're using runs in Mono. We're not using any Windows forms or anything like that. It's all command line. The tool is released under GPL v3, the latest draft, which is 2. And some of the other reasons we use C# is it's very similar to C++. Most of my development has been in really assembly and C, and so this is in a little C++. So it's kind of cool to learn a new language, and it was also nice that since it was sandboxed, we can use a lot of the built-in exceptions to catch some of the overflows. So we'd use stuff like create buffers to emulate the stacker and whatnot, and if there was if we're writing past a certain location when we emulate an opcode, then the .NET catches it and throws an exception, and we trigger on that exception. So targets of detection. A lot of vendors have their own definition of what an exploitable bug actually is. If you talk to a vendor, sometimes they'll say, like, depends what you mean by exploit, depends what you mean by bug. Because they're trying to up their numbers and say that, they catch this or they catch that. All we're looking for, our definition right now, is an out-of-bounds memory write using user-supplied data, tainted data. Doing out-of-bound reads can be vulnerabilities. Let's say you're able to read password files, hashes, variables, other types of logic from memory, that's definitely a vulnerability, but right now we're just concentrating on writes. And you can also, at times, maybe do an out-of-bound write without tainted data, like you terminate a null, and that causes, let's say, a heap overflow, and it changes the lowest byte. You could do things like that, but all we're doing right now is tainted data. It's the easiest thing to trace through, and I'll show you how it works. So we have, part of our tool comes with a lot of system tests. The whole tool was written with using like test-driven development, so we have lots of unit tests within the tool to test the functionality, and then we have system tests, which are really just simple C programs that have something comes in from argv, you malloc like 16 bytes, and then you write to position 16 in the buffer, so you write one past the end of the buffer, stuff like that. And then we trigger on stuff like that, and then we keep on cycling through tests. So every time we add a feature, we make sure that everything that we've done in the past still passes. Looking at some other vendors' products and whatnot, at times they'll issue an update, and things that they used to catch, they won't catch. Things that they didn't catch, they catch now, so there's no way of controlling quality. So this is one reason that we did it this way. So this is the architecture. Basically, it's a set of tests that is part of the project. They're all on the part of this version tree, so you can check those out and see how they work. Then there's a core x86 emulator that's separate from the analysis engine, because we want to be able to do, let's say, ARM later on and different processors. So we're really trying to modularize it so that analysis and the processor-specific code is separate from each other. So these are some of the challenges, some of the problems that you encounter when you're doing this type of binary static analysis. One is branches. When do you take a branch? When do you not take a branch? You don't know all the data that's coming into your program. So certain decisions have to be made about what kind of state comes into the branches, what kind of state leaves. Something else that's really important is inner function analysis. No longer are we going to have a single function going to be the vulnerability, and everything is there. The only time that happens is like sample programs that show you how buffer overflow works. Nowadays, you're going to have data coming in from a user somewhere else, and then it gets fed up a call chain, and then the vulnerable function is way somewhere else. Something else that has proven a little difficult sometimes is non-continuous functions. Most new compilers, like I think SP2 was all compiled with 7.1, which is Visual Studio 2003, that has non-contiguous functions, and everything from there on does. If you do a lot of reversing of Microsoft stuff or patches, you'll notice it, lots of non-contiguous functions. Something else that can be a problem is self-modifying code, which, I don't know, we don't really care about, because we're looking for vulnerabilities in vendor software, and I don't know any vendors that I want to own that use packers or, self-modifying code. Usually it's just straight code. And something else that can be a challenge is loops. Loops sometimes can be difficult because it requires a little bit of like an algorithm to analyze if it's going to overflow something, if it's a bounded loop, if it's an unbounded loop. And something that we've done specifically for this project is we've taken different compilers, we've taken different optimization levels, and we run each test through each of these levels. Because you don't know like what switches different vendors are going to run in. So we're trying to really make it generic so we can tell what's going on and not have not rely on, let's say, one version of a compiler or certain sets of switches. Some other vendors have done things like that, and it doesn't really work very well. So dealing with branches. There's two possibilities. You have a known value. If you have a known value, it's easy. Let's say you're comparing, there's going to be a 0 coming into a basic block, and you're comparing, EAX is 0 and you're comparing it to 0, you know what's going to happen. One machine state is going to come out of that. If you have unknown values, you don't know what EAX is, you don't know what's being passed to that function. It's coming off the network or whatnot. It's part of a buffer coming off a network. It could be anything. Then you're going to have, for every compare before a branch, you're going to have 2 machine states. And you have to decide, what are you going to do? Are you going to follow one path? Are you going to follow another path? Are you going to follow all the paths? This can become problematic as things start to explode out on how many different combinations there are. So one thing that we're using is constraints. Constraints is a way to say a certain unknown value has a certain range based on calculations that were performed to reach that level. So if you did a comparison earlier and it said there was a branch and let's say it said less than 5, and then you see another comparison and it says greater than 8, you know it's not going to be greater than 8 because you got there through less than 5. So things like that. I have code examples that'll show that a little more clearly, but constraints is basically a way of being able to have a range of unknown values without actually knowing exactly what it is. So when you're dealing with branches, the jumps, the SBBs, all that, don't really decide what happens based on input. Those are all reactions based on the compares, the test, math instructions, and whatnot. Those set flags, those are the things that cause the different machine states to appear, the different combinations. And the jump, the like J and E, whatever, because this is all x86, so that's what I'm using right now, is all based on the comparisons and the flag conditions. So branches really come down to comparisons and the results of comparisons. So here's a little bit of like pseudo assembly. So in line 1, we compare EAX with 0, and if it's not 0, in line 2, it's going to jump to 4. So line 4. So coming into this, if we get to line 4, we already know that EAX is constrained. EAX cannot be 0. So we already know certain things about EAX. And you start doing these type of things, and you start gaining more knowledge about what values can be through certain paths. And all these different paths each basic block describes a transformation or a path that it goes through. There's an input state into a basic block, and there's an output state. And you start combining these things together, as we'll see later, and functions basically are just that. They're basic blocks which are transformations of input and output strung together into a big expression. So how do you choose branches? You could cheat. You could follow all branches and see what happens. See, it's going to take you down a certain code path. You're going to be able to analyze part of the program. You're going to have some code coverage. Something else you can do is randomly pick branches. That'll probably give you more code coverage. You'll go through more of the code. You can also take every branch. So every time you hit a comparison or a branch, you take both sides. Eventually, this is going to get really big. It expands and expands and expands. Real software is going to have tons and tons of branches. So option 4 is to take some branches. So somehow decide which ones you're going to take based on certain constraints or certain things that you want to test. You want to test maybe really small values, really large values. Maybe you want to test -1. Maybe you want to test 260, which is like the max path in Windows, or maybe 259, which is one less. So you can try to limit it based on knowledge that you've acquired from other vulnerabilities. So in choosing branches, a lot of functions are going to have guards at the beginning. Like, let's say you're passing in a pointer. It's going to check if it's null right at the beginning, and if it is, it's going to return right away. So usually in the assembly, guards are going to drop through.